Hello everyone, and welcome to the two-dimensional projectile motion post-lab. So in the pivot interactive that you completed, we were able to take a two-dimensional projectile motion and split it up into horizontal and vertical parts. As we discussed in the pre-lab, those parts are independent of one another, and so we can kind of analyze them independently, right? Which gives us a technique for solving a two-dimensional problem, right? So what we were looking for was to identify the kind of motion that we saw horizontally and vertically. So let's start out with the horizontal motion of a two-dimensional projectile. And again, that means no air resistance, right? Just gravity. So when you graphed the position as a function of time, notice me using an X here because this is horizontal position. What'd your graph look like? Well, hopefully it looked like this. And it was a nice linear graph, essentially going through 0, 0. Well, what does that mean? Well, let's check out the slope. As this is a graph of horizontal position versus time, what does the slope tell you about the motion of the ball horizontally? Well, the slope of a position-time graph is the velocity. So this is the horizontal velocity, is this slope. Was it a positive or a negative? Was a positive slope, which goes with the direction of the velocity. In the pivot, the ball was going from left to right. It was going to the right, which is positive direction. And was the velocity of the ball horizontally increasing, decreasing, or constant? Now be careful here. I didn't say the position. I said the velocity. And the velocity is the slope of the graph. And the graph is linear. So that means the horizontal velocity was constant. I didn't have you make a velocity time graph inside of horizontal velocity time graph inside of graphical analysis. Instead, I just asked you to sketch what you thought it would look like, right? And since this is a constant positive horizontal velocity, there we go. Right? A horizontal graph is a constant, right? It's the graph of a constant. And notice my use of Vx. So the x is a subscript, means horizontal. If it's a y, it's vertical. If it's x, it's horizontal. So it appears that for two-dimensional projectile motion, the horizontal velocity is simply constant velocity motion. Well, at least that's what it seemed like experimentally. Let's theoretically analyze this. So if this is our ball somewhere along its path, after she throws it, before it hits the ground, what forces act on the ball? Well, if it's projectile motion, gravity, down, and that's it. Now we're looking at the horizontal part. So what is the horizontal net force? See my little X here, right? Well, look at the force diagram. Are there any horizontal forces? No. So the horizontal net force is 0. And if you don't have a net force, what's your acceleration? 0. Notice AX, so that's the horizontal acceleration. By the way, if you don't know what this is, it's a kind of a geometry thing. Those 3 dots in a triangle like that mean therefore. So you would read this as therefore, the horizontal acceleration is 0. And if your acceleration is 0, what kind of a velocity do you have? Of course, that means constant velocity. I didn't have you draw the acceleration time graph because it would have been pretty boring. It just would have been right on the time axis because it's 0. So this is a little proof here, using Newton's laws, that we should have constant velocity horizontally because we have no net force horizontally and therefore no horizontal acceleration. And sure enough, that's what we actually found inside of the pivot. If you remember when we analyzed this motion back in one of our very first labs, which was the toy car lab, beginning of the year, we found one equation that we could use to describe constant velocity motion, and that was this. Horizontal displacement, final minus initial horizontal position, right? Horizontal displacement is horizontal velocity times the time. You'll notice me putting a little X here because I want you to remember that this is the horizontal. This is really just displacement is velocity times time, right? Which is just constant velocity. No big kinematic equations or anything because there is no acceleration. Now, oftentimes when we're talking about projectiles, and throwing something or shooting something off, we often want to know this quantity, all right, the horizontal displacement. We often want to know how far does it go, but we often don't use the technical, what is the horizontal, I kicked a soccer ball, what was its horizontal displacement? You might say that, right? You might say, how far did it go? But you also might call that the range. This is sometimes known as the range equation. Right? That's especially true when you're doing ballistics. Right? If you're shooting off a cannon, you'll often talk about, well, what's the range of the cannon? And you don't mean how high up it goes, or what's the distance along the parabola that the projectile travels. You mean, how far did it go horizontally? Right? Like, where's it going to land compared to where you shot it from? So this is an important little quantity here. So from a vocabulary standpoint, the technical terminology is horizontal displacement, but you might also hear things like range, right, used in that case. So this is the horizontal half of the motion, just simply constant velocity. But what about the vertical part of the motion? Well, you looked at that ball from an end view going up and down, and you graphed the vertical position as a function of time, right? Let's see the y here. And didn't you get a full-on parabola, basically? Yeah, it didn't start down at 0, 0. It started up here because it was up in the air, but you basically got the parabola. Notice that with this pivot, we're in the first quadrant because we called the ground 0. So the ball was always above the ground, had positive values of position. Right, so that's why we're in the first quadrant here. I then had you turn this into a velocity time graph by doing the slopes of the tangent line deal that we can do inside of graphical analysis. And you got a vertical velocity, v sub y, as a function of time graph that looked like that. We've seen that before. Here it's going up and slowing down. 0 at the highest point. Right, this is the highest point, the little dotted line. And then on the way down, it's going in the negative direction and speeding up. But let's talk about this graph, and in particular, let's examine the slope of this velocity time graph. Being that it's a vertical velocity versus time graph, what does the slope represent? Remember, every slope is a rate of change, so this is how quickly the velocity is changing, which we call the vertical acceleration. In this case, is it a positive or negative? Well, the slope is clearly negative. And is the acceleration, the slope of the graph, increasing, decreasing, or constant? I didn't say the velocity, right, of the ball, which is actually decreasing on the way up and increasing on the way down. Right? I meant the acceleration. Well, since the acceleration is the slope, and this is a linear graph, the acceleration is constant. Or as we've called it in the past, the more fancy, uniform. So we see experimentally that this ball vertically had a uniform negative acceleration. And when I asked you to draw the graph that would go with that, right, it should look like that. Now, that's what we found experimentally. What about theoretically? Well, let's start out with, again, the force diagram of the ball. After she threw it, before it hits the ground, the only force acting, the downward force of gravity. So is there a net vertical force? Not horizontal, right? Vertical. Yeah, because nothing is balancing out gravity. So there is a net vertical force. And we know from Newton's second law that net forces are equal to mass times the acceleration. Now, since this is the vertical net force, this will be the vertical acceleration. But we only have one force, that's gravity, and it's down, which makes it negative. So the net vertical force is negative F of g. And as we've done many, many times, we can rewrite near the surface of the Earth the force of gravity as mass times the gravitational field strength. And this is where we do the very important, seemingly simplistic, but actually very deep thing of saying, hey, look, mass here, they cancel. Remember that this means that more mass means a bigger force of gravity, which would have a tendency to accelerate it faster. But more mass also means more inertia, resistance to changes in its motion, which would tend to mean it would accelerate slower, and those two things cancel out. Not a good reason for those two things canceling out in Newtonian mechanics, but yet they always do. It's a much deeper idea of general relativity, right? But we can cancel them out here, right? More mass means more gravity, but more mass also means more inertia, resistance to changes in its motion, which means that our vertical acceleration is just equal to our gravitational field strength, or negative 9.8 meters per second squared near the surface of the Earth. And because there's no time in here, it's a uniform acceleration. As long as gravity is constant, it will give rise to a uniformly accelerated motion. Now in the pivot, you probably got an acceleration a little closer to negative 10 or a little bit more. And that threw me a little bit when I did the pivot myself. It's like, how come it wasn't, really close to negative 9.8 like our other pivots were? And at first I thought, well, maybe the ball had some air resistance, but that didn't seem to check out for me when I looked to see what the answers were compared to what I thought they'd be. And then I realized, oh, okay, the problem with this has got to do with the way they made the video. It's a matter of perspective. While we were measuring the up and down motion of the ball, right, from an end view, it was actually moving a lot closer to the camera than it started out, right? Because it was also moving horizontally. And so that's throwing off like our ruler that we used, because our ruler is really only going to work at kind of one distance away from the camera, right? If you think about how a video works. Normally when we've done these, right, the object in the video is moving kind of in one plane, and then our ruler lives in that plane, right? Everything's the same distance away from the camera, right? Like when we were doing one-dimensional projectile motion and it went straight up and down. Well, in this case, the ball was moving several meters closer to the camera than it started out at the beginning. So that kind of threw off the data. So it didn't really matter how well you did it, all right? So you're going to have to buy that the negative 10 was about as close as we could get to the negative 9.8 without doing something even fancier with this graph. But I thought, close enough, right? That's still a couple of percent, which is pretty close to this. Sometimes in the concept builders, you can just use negative 10, right? It just allows you to do that. So that's why we had a little bit of error. But since this is uniformly accelerated motion vertically, well, then our old friends, the kinematic equations, come back. Note how I've used the y's because this is vertical. So these are final vertical velocity and initial vertical velocity. We now know the acceleration is going to be our old friend negative 9.8 meters per second squared, or little g, instead of a. And this is the vertical part of the motion, so this is the vertical displacement. Now, I was trying to get you to write them out this way for the last couple of pivots and worksheets and things, but if you've still been using, the X's and the A's and things like that, you might want to try to write them out this way, because now we have both flavors of motion, right? We have horizontal and vertical in this case, and we need to keep them separate because they're different kinds of motion. So notice here that both experimentally and theoretically, it appears that the vertical motion of a two-dimensional projectile is uniformly accelerated motion, with a special acceleration near the surface of the Earth of negative 9.8 meters per second squared. Put the two together, and that means we can see that two-dimensional projectile motion is really just a combination of two models that we've already spent a lot of time learning. Horizontally, it's constant velocity. And mathematically, we only need one equation to describe that, right? Displacement, horizontal displacement, is horizontal velocity times the time. Or, remember, this is range, right? This is the range. Vertically, it's uniformly accelerated motion with an acceleration of little g, or negative 9.8 meters per second squared, and which means we can use the three kinematic equations. You put these equations together and you get the two-dimensional projectile motion parabola, right, that an object with only gravity acting on it undergoes near the surface of the Earth. This makes parabolic motion. Right? Galileo Galilei was actually the first one to figure this out. He was the first one to realize that projectiles actually move in parabolas, and he realized that it would move in a parabola if the horizontal velocity was constant and the vertical velocity was uniformly accelerated. Now, he didn't have Newton's laws because Newton's come after Galileo, right? Isaac Newton was born the year that Galileo died. So he had to kind of think through this in terms of motion and what these two motions would look like together. He actually did it with some pretty complex geometry, all right, to prove this. And obviously he didn't have videos where he could use drones and head-on views and different things like we did to kind of get fancy and break the motion apart into horizontal and vertical parts. He had to kind of think his way through it. It's really kind of incredible that he could come up with that. And once you get to Newton, then you could prove why. You could explain why it was constant velocity horizontally, because there's no net force horizontally, and uniformly accelerated motion vertically, because gravity's the only thing acting, therefore there's a net force. Put the two together and you get a parabola. So this is a little GIF that I stole from the concept builder guy. Borrowed from him, right, with permission. As you watch this ball, what he's done here is he's kind of animated most of a motion map. The dots represent positions of the ball at equal intervals of time. But instead of drawing a single velocity arrow, he drew out the components, which is kind of traditional to do. So you can see the horizontal component of the velocity and the vertical component of the velocity. Okay, now he didn't draw an arrow for acceleration, but that would be constant pointing down anyway. Now this is a special case, and it's a special case we're going to talk about for the next couple of days and eventually even do a little practicum on. And the special case is this cannonball is being shot horizontally off of a cliff. It's not being shot at an angle. That takes a little more math. We'll get to it. It's being shot horizontally. So I want you to notice a couple of things, sorry. First off, notice here as you watch the GIF that every dot is about a second, right? Well, look at the horizontal velocity arrow. Watch it as it goes here. What do you notice? It stays the same size the whole time, right? Well, why? Well, because as we just showed experimentally and theoretically, the horizontal velocity is constant. Right? So the arrow stays the same size. And if you look down there, it leaves the cannon going 100 meters per second horizontally, and it keeps going 100 meters per second horizontally. If these actually had, numbers, after 1 second, it would have gone 100 meters per second. After 2 seconds, after 1 second, it would have moved 100 meters. After 2 seconds, it would move 200 meters. After 3 seconds, it would have moved 300 meters horizontally. Vertically, though, the motion is more complex because check out the vertical arrow. Watch this. You see how it's getting longer and longer and longer? That's because the velocity is changing. It is accelerating. And you might notice that he chose to use the simpler 10 meters per second every second. See how this goes up by 10 meters per second every second that goes by? It's a clever little GIF. By the way, one special thing. The initial velocity, when it comes out of the cannon, is completely horizontal, right? Because the cannon is pointing horizontally. So what is the initial vertical velocity? Watch. Do you see how at the first dot, there is no, and watch down here too, it says 0 for 1 second, right? There is no vertical velocity initially. This is our special case. If something is projected, kicked, thrown, whatever, horizontally to start out with, its initial vertical velocity is 0, right? Because if something's shot horizontally, there is no vertical in horizontal. Now, it doesn't stay that way because gravity's acting vertically, and that makes it accelerate vertically, but it starts out that way. Right? So we're going to spend a couple of days where this is going to be kind of our special case. Then we'll go to projecting something at an angle, in which case it'll have both horizontal and vertical components initially. It'll be shot out horizontally and up or down. But in this case, all horizontal, no vertical to start with. Right? So the vertical velocity is constantly accelerating. Now we're going to do some, concept builders and, like I said, a practicum and a worksheet here just to start to get all of these things in your head, right? So again, it's not two-dimensional projectile motion really isn't a new model. It's a combination of two of our previous models, constant velocity horizontally and uniformly accelerated motion vertically.